So after this, you just expand your potential. Your potential, this is harmonic potential. This is just one extra term. Okay, so this is the potential from the Duffing oscillator and the electric field. So the force, the newtons, the dimension of force is Newton, is QE. Q is this electron charge, E is electric field. So the dimension is correct here. And we can rearrange the constant so that you can see the P double dot alone on the right hand side. And here the d over dx, we just work it out as usual. And then you change the constant, or okay, for example, you change the constant, and so you have to, let me see. So when you change the constant, you have to be very careful. Okay, so this one you call it kappa, and then this one you call it beta. So this is the equation of motion from our system based on Duffing oscillator. So the electric field is EZT, and then we make it into complex form with 1/2, the half year. Okay, so here there are, okay, here I play with the constant. Okay, I multiply every term with this constant, so I can make the P double dot alone. So this is the equation that equation motion that we are going to use to derive. But we don't want to use the dot. We convert the double dot to d square over dt square. P dot become dp over dt. So this is the equation that we use. So I highlight this term. Okay. So while I'm talking, you can take the photo in progress. All right. So from electricity and magnetism, if you have a driving field, okay, so this P is the polarization is induced by the E. So once you have the E, definitely you have P. So whether you have the linear P up to here, or you have nonlinear P like this, is due to the strength of this. Okay, you can see what I highlighted, the amplitude of the E field. You know that this time dependent E field, this is the time dependent parts. How strong is the field is depend on the amplitude. So this is how is it. If this is small, you can throw this part away. If this is strong enough, you must retain this. If you have this one stronger and stronger, you have more terms. Okay, you must have plus P to the of 5 and so on. So we consider this is strong enough to excite these nonlinear terms. Okay, so from your basic electricity and magnetism, you have the P equals to epsilon naught chi E. So last week I confused with whether I should put epsilon naught or not. So I refer to Morgan. So this is the last year final projects, the articles they refer to. So you can see this article. Later after the meeting, I will send this paper to you to your email. Is it okay? So you can see how they are doing. So we follow this article, but of course you're not doing ferroelectric. We are doing general simple nonlinear medium. Okay, but how you treat the electric field is useful. Let me see. Okay, so you can see this is the P when nonlinearity excited. Your P is not simple P1. You have P2 and you have P3. So your P1 is epsilon naught chi ILEL. Your P second order P, nonlinear P in second order is epsilon naught chi 2 EE. And the third one is epsilon naught chi 3 EE. So you look at the linear, you have only the you have 2E, and then third one you have 3E's. Okay. I have to be very careful of the time. Okay. So we come back to this. So we follow the articles. Okay. So because of the third order terms here, so our P equals to, we let it expand until third order terms. The higher order terms we don't consider. So our P1 is epsilon naught chi1 E. P2 is epsilon naught chi2 E. P3 is epsilon naught chi3 E. Okay, and then we have these are all P. These are all P, no problems. But this one you have P3, P to the power of 3. Okay, so P3 you have this term to the power of 3. So you can see this one, this is our P, this is our P, and then this is our P. But we want just the up to third order term. The third order term from these products is P1, P1, P1. Okay, because you have many combination. You can have P1, P2, P1. But if you look at the P1, P2, P1, P1 you have 1E, P2 you have 2E. If you go back to, if you have P1, P2, P1, you have E to the power of 4. So remember, we want to cut until third order effects. So if the E more than 3 terms, we discard. So these products, only one term has three E's. All the other terms has at least 4 E's. 4 E's. So we have to discard. So the T to the power of 3, we have to retain only one term. Okay. So now we work it out one by one. We have to work out the P1 first. We work out the P1, P2, P3, and after this, we only substitute into the equation of motion. After this, we substitute into here. So our P1 is chi epsilon naught chi1 E. So you substitute your E like this. Okay. You substitute your E like this into here. Okay. Here I highlight in some other color. Green. Okay. So the green here, P1 equals to epsilon naught chi E. Okay. So when you substitute, you have this one is the simple chi. This one is the simple chi1. This is a general formula, is okay. But when you really expand it, you have to be very careful of the terms. Okay, so when you substitute the terms, the chi1 becomes split like this in complex notation. So here I drop the star. Last week we had the star, right? Okay. So okay, you don't have the star here. So last week I put the star on the chi, but now the star only on the amplitude of the field. The star is no more on the chi, but the complex conjugate you can reflect it in the argument. So this is the complex term. This is the complex conjugate. Okay. This one is the complex term. This is the conjugate. Okay. This term is the conjugate of this, and this term is the conjugate of this. So the whole term on the right is the conjugate of this. Okay. So when you write like this, then things is perfect. Okay. So the chi for the complex term is like this. This is the conjugate. So you can see how I write. The negative omega here is here. And the sign here is semicolon, not comma, semicolon. Semicolon. And the positive here